Hello, Emanuele.
Hi, my name is Emanuele Piccoli and I work at EMPA, which is the Swiss Federal Laboratories for Material Science and Technology. Well, this is already exciting for me. I am a doctoral student and the HyCool project gave me the opportunity to work with experts in the field, which otherwise would have been very difficult to work with. Just to mention a few, I've been working with pleasure with people from CNR, ETA, but also from Fahrenheit. And yeah, I would say that also overall, to be involved in a project with such a positive potential impact is very satisfying. In our lab, we developed for a long time nanoporous materials for several applications, collaborating with both academia and industry. Our team is in charge of selecting the best adsorption material for the HyCool Hybrid Chillers and to monitor their possible performance degradation.
In your own words, what is HyCool?
HyCool is one of the most promising industrial solar cooling solutions developed so far. With the support of the European Commission, we are combining solar collectors and adsorption chillers to provide steam, heating, and cooling energy with greater efficiency.
Why do you think that this project is important?
In projects like HyCool, where over 10 partners work as one, they really are a unique opportunity. It is the perfect place where synergies can be built between excellencies already existing across Europe. For example, it is a huge chance to enhance the communication between researchers and engineers, which is exactly what innovative solutions need to be developed. This type of project is exactly what is needed to develop a new sector, such as industrial solar cooling, from kickoff to competitive solution.
What is EMPA's innovation for the HyCool project?
EMPA, as it is in its mission, is looking at the future. We are performing scientific research to push HyCool efficiency to the next level, specifically the one of the adsorption chiller. In particular, we are finding ways to better use state-of-the-art adsorbent materials and way to integrate new materials, possibly more performing. More specifically, we are developing a computational tool to simulate and predict the performance of adsorbent materials in a given industrial application. At the same time, giving feedback to the material scientists on how to improve this material.
Why is EMPA's innovation interesting for the industrial sector?
The benefit of the simulation tool I mentioned, I would say, is twofold. Firstly, it will help cooling technology developers, such as our partner Fahrenheit, to develop even more efficient cooling technology. Secondly, it will considerably shorten the time from lab to market of novel materials.
What is the purpose and the reason of your work package 4?
In the HyCool system, part of the solar heat is used to produce cooling through the adsorption and regeneration of a nanoporous adsorbent material. As the name suggests, this adsorbent material is the key of the adsorption chiller. So it is defining its potential, but at the same time, its limitations. This work package is meant to find the best possible material for any given application and to make sure that its performance is reliable over time. Now, the way an adsorption material works when integrated into adsorption chiller is as follows. During the evaporation, so when the cooling is provided, the heat transfer fluid is evaporated from the evaporator and is being adsorbed onto the surface of a nanoporous material which has an incredibly high surface area and pore volume. When the vapor deposits on its surface, there is a phase change and a huge amount of heat is released, and it will be discharged to the environment. To regenerate this material, another phase will be necessary, in which the material is heated up and therefore dried, giving vapor to condensate in the condenser as it would happen in a conventional chiller. In this way, it is possible to go through cooling and adsorption and drying and regeneration in successive steps.
Why is the HyCool project the best framework to aim at this purpose?
Well, thanks to HyCool, we can really work as a team. EMPA, with its history of nanoporous material development, surely can understand very well the issues and the perspective of material scientists. However, the coordination with other partners coming from cooling technology development, such as Fahrenheit or CNR ETI, it's absolutely fundamental. Just to give an example, CNR has a huge knowledge about material testing and its degradation, while Fahrenheit really know what will be the conditions in which this material will operate. And therefore, our joint effort is much more significant.
What are the specific problems or challenges that are being faced by EMPA?
For adsorption chillers, often the limitation was from the material use itself. The volume of these devices and their cost was often prohibitive, and sometimes the scaling up didn't deliver the expected result. Some of the reason behind this is that the sector is not yet fully standardized, and a simple but yet accurate description of the adsorption process not fully available. In fact, due to these peculiar materials that are involved, the performance of the whole chiller is strictly related to the material properties, and the process is happening at a very small scale in the micrometers range.
What are the specific activities that are being developed to tackle these problems or challenges?
Well, at first, we developed a material characterization protocol, which provides the basis to evaluate candidates across different labs in a unique and comparable way. This provides to be very helpful to avoid misunderstanding on the material properties. As a second action, we gathered as much information as possible on the adsorber material available right now on the market and screened their potential applications. A further action was to develop a model able to predict the potential performance of these materials once integrated in the heat exchanger. This is fundamental to correctly integrate these materials into the heat exchangers and to make the most out of it. At the same time, this is fundamental to give feedback to the material developers to improve their materials. At last, we want to make sure that the predicted performance will be reliable over a long time. Therefore, we are testing the materials in very challenging applications, and if any degradation will appear, we will provide mitigation strategies.
And how do the results look so far?
The results look very promising so far. The protocol proved to be very effective in eliminating misunderstanding regarding the material properties. And currently, we are completing the test of our performance model. But it seems that it can provide a reliable description of the adsorber material performance in terms of both energy efficiency and achievable cooling power, which will in turn be very useful for further material development.
From your perspective, what did we achieve and how does it translate to the project stakeholders?
During the last few years, we gathered a lot of information about the materials that are available in the market, and we reached a good understanding on their potential performance. And once we will publish our model, basically anybody will be able to do the same with their materials, which means that in a very early stage of development, they can compare the results with the solutions available in the market and point the research and development effort into the right direction. This means that in the future we will have a wider and more competitive catalog of industrial solar cooling solutions available. That means that in the bigger picture, we are supporting the development of adsorption technology as a whole, which means that more people will be able to afford sustainable energy, big and small companies alike.
How do you see HyCool's solution in the future?
There is a huge societal and climatic pressure on the decarbonization of the European industry. So we will definitely need HyCool, and HyCool will be there. Looking at the progress obtained over the last few years, I have no doubt that, especially in the sunny regions of the world, it will be very hard to say no to this solution.
Thank you so much, Emanuele, for your time, and thank you for your interview.
Thank you.